Hello and welcome to lecture 37 on the calculus of polar curves. So you're going to find that luckily this is very similar to our lecture on the calculus of parametric curves. So we're going to do the same kind of calculus things, but we're just going to put it in the framework of polar curves. I'm going to give you relevant formulas for the same ideas. So let's take a look at this first idea. So in calculus, finding the tangent line is a very important concept. So to find the tangent line to a particular polar curve, you regard theta as a parameter. And we're going to start by writing our polar equations that we learned in the polar section of this course. So x is equal to r cosine theta. And then here we have a function r equals, and it's some function of theta. So this r right here, I can replace that with f of theta based on the way I'm defining this. So this will be f of theta cosine theta. And then for y, recall that the polar formula is r cosine theta. And again, I can rewrite this as f of theta sine theta, just based on this equation right here. So now let's take a look at what the formula for the slope would be. So we're going to proceed in a very similar way that we did with parametric curves. So this is equal to dy d theta over dx d theta. And if you recall from the the parametric section, it was dy dr over dx dr. So this time, theta is in the place of r. It's our parameter this time. So that's what I mean when I say theta is our parameter. OK, so let's take a look at this. I need to figure out what dy d theta is. So that means I need to take the derivative of y with respect to theta. Well, what rule would you use if you need to take the derivative of this with respect to theta? You'd use the product rule. So the product rule with this is going to be f prime theta. So that's the derivative of the first one. We rewrite the second one. And then we're going to do plus, and then we switch the order. So we're going to leave the first one alone for the product rule, and then times the derivative of the second, which is cosine theta. And I'll do the same thing for this equation right here. So for the derivative of x with respect to theta, for this I'll do the product rule. So you're going to get f prime of theta, and we're going to leave cosine alone. And then you actually get a minus because the derivative of cosine is negative sine. So you're going to leave f of theta alone, and then the derivative of cosine is negative sine. And then finally, what I could do is I could rewrite this in different notation. So what is f prime of theta? Well, it's the derivative of this, right? F prime of theta is the derivative of f. So actually what we have here is we have dr d theta. That's another way of saying the derivative of this with respect to theta is dr d theta. So that's another way to write this. And then I'm just going to copy over my sine theta plus what's f of theta? Well, that's r. And I have cosine theta. And then very similarly in the denominator, I have dr d theta times cosine minus, and this f of theta is r, times sine. So this will be our formula for the slope of the tangent line when you're given a polar curve in terms of theta. So I would maybe make a note card of this. So this is how you find the slope of the tangent line. Now what we can do is we can ask the same question we did earlier in a previous lecture. Where do the horizontal and vertical tangent lines occur? Well, you'll do the same kind of thing. You're going to need, for a horizontal asymptote, you need the numerator of this to be 0, because you want the slope to be 0. So what we need is we need dy d theta to be 0, and then provided we can't have dx d theta be 0 at the same time, right, because that would be undefined. So to find the horizontal asymptotes, what you're going to do is you're going to set this numerator, which is dy d theta, equal to 0, because that's where the slope is 0. So I'm going to write slope equals 0. And then here for the vertical asymptotes, you set the denominator equal to 0. So a very similar thing that we had from before. So this is dx d theta should be 0. So that's where the vertical, the tangent line is vertical. And then this is also provided that dy d theta is not 0 at the same time. And as I mentioned in a previous video, if that were the case that they were both 0, you'd need to use L'Hopital's rule to then determine what's going on with the slope. All right, so let's do an example of this. You may want to pause the video because this is so similar to those parametric problems, and just try out the formula yourself and see how far you get, and then you can check your work with me. So we're going to find the slope of the tangent line to this polar curve right here. So this is our f of theta. We're going to find it at a particular spot at theta equals pi over 6. And then later we're going to find where the horizontal and the vertical tangent lines are on this particular interval from 0 to pi. All right, so let's write our formula for dy dx. So it's this right here. It's dr d theta sine theta plus r cosine theta divided by dr d theta cosine theta minus r sine theta. Start plugging into this formula. What is dr d theta? That's the derivative of r right here with respect to theta. So the derivative of 3 cosine theta is negative 3 sine theta. So that's going to go in for dr d theta. And I'm going to plug that in the denominator as well because we have the same thing right there. So this is negative 3 sine theta. I'm going to multiply that by sine plus, we have to plug in what r is. So r is 3 cosine theta, that's given. So this is 3 cosine theta times cosine theta. Here I have cosine theta, that's next to this dr d theta, minus r is 3 cosine theta, because that's what's given over there. And then I will multiply that by sine theta. Now let's make this look a little nicer. So I'm going to write this. Notice that every single 3 cancels out, right? All of these terms, all 4 of the terms, have a 3. So all of these 3's cancel out. I'm going to take care of that now. And I'll get negative sine times sine is negative sine squared. Looks like I have plus cosine squared divided by, and I have negative sine cosine minus sine cosine. So I have minus 2 sine cosine. Now we're going to have to plug in pi over 6 because that's the point we're given to find the slope at. So we want to know when theta equals pi over 6. The two things I need to know is what is sine of pi over 6 and what is cosine of pi over 6. So maybe off to the side down here, let's recall that cosine of pi over 6, that's the same thing as root 3 over 2. And then sine of pi over 6, that's the same thing as 1/2. So you're going to have to know your unit circle stuff to do this lecture, so make sure you review that as well. So everywhere I see a sine, I need to replace it with 1/2. And everywhere I see a cosine, I need to replace it with root 3 over 2. So let's do that. So here I get negative. Sine is 1/2 squared plus. Cosine is root 3 over 2. That's also squared divided by. Here I have negative 2. Sine is 1/2. Cosine is root 3 over 2. And this now becomes just an exercise in simplification. So what can you do to make this as easy to simplify as possible? Well, let's just go piece by piece here. I'm going to do negative 1 over 4 plus this would give me 3 over 4. Notice I have a 2 and a 2 that cancel. And I get negative root 3 over 2. To make this look even better, I'm going to multiply the top and the bottom by 4 over 4, just like that. So I'll get negative 1 plus 3 over 4 over 2 gives me negative 2 root 3. It's looking better. It's just a matter of taste, I guess, when I stop. This will be 2 on top, and there's a 2 down here. So I'm going to get 2 over negative 2 root 2, or negative 2 root 3, sorry. And if I cancel out the 2's, I get negative 1 over root 3, which is, if you rationalize the denominator, it's the same thing as negative root 3 over 3. So, I mean, I'm finally satisfied with how that looks, but we were good probably over here. We were OK. So you could think of this as the slope of the tangent line. Now what I'd like to do is I'd like to figure out where the horizontal and vertical tangents occur. So remember, for horizontal tangents, what I need to do is I need to set dy d theta equal to 0. So when I do that, dy d theta was this top portion right here. It was negative 3 sine squared. So I'm looking at this whole numerator. That was dy d theta, plus 3 cosine squared theta. And we just have to solve this trig equation any way we can. Divide the 3 out, and you're going to get 0 equals negative sine squared plus cosine squared. Add the sine squared to the other side, so we get sine squared is cosine squared. What could I do here? Well, what I'll do is I'll convert the sine squared into 1 minus cosine squared. And then what I get is if I add the cosine squared to the other side, I get 1 equals 2 cosine squared. And I'll continue over here. That means 1/2 is cosine squared, which if I take the square root of both sides, I get plus or minus the square root of 1 over 2 is cosine. But then that's the same thing as plus or minus root 2 over 2 equals cosine theta. So if we're just focusing on the interval from 0 to pi inclusive, so remember, we're focusing on 0 to pi inclusive, where are the two spots where this occurs? Well, cosine is root 2 over 2 at pi over 4. That's one of the spots. The other one is here at 3 pi over 4, where this is going to be negative root 2 over 2. So the two thetas I need here are going to be pi over 4 and 3 pi over 4. And then what does this tell me about the coordinate? What I would need to do to write the final coordinate of where the horizontal tangent occurs is I need to find the r value, right? So here's the 2 points that you get where you have the horizontal tangents. If you plug in pi over 4 into the original curve, you get 3 times cosine of pi over 4, which that's root 2 over 2. So one of the points is going to be 3 root 2 over 2 pi over 4. The other one, if you plug in the 3 pi over 4 into this, you're just going to get negative. It's going to be negative root 3, or negative 3 root 2 over 2. So these are the two spots where you have the horizontal tangent lines. We can do the same thing for the vertical. You should pause and try it if you haven't already, if that made sense, what I just did. But I'm going to go ahead and do this now. So what we need this time is we need dx d theta. That needs to be 0. Well, that means I'm going to set the denominator equal to 0. I'm going to use this simplified version of it right here, because I have it here. That's my dx d theta. But I'm just going to use the simplified version, which is negative 2 sine theta cosine theta. So now, notice that I could divide the negative to the other side. I'll get 0 equals 2 sine theta cosine theta. But that's a formula that I should recall from much earlier in the semester, right? 2 sine theta cosine theta, that's sine 2 theta. So doing that makes this a lot easier, because now I need to know 2 theta needs to equal the angles where sine is 0. So if you're thinking about the unit circle, where are the angles where sine is 0? Well, it's at 0 and pi. That's where you have 0 for the y coordinate. So this 2 theta here, I need to make sure that that's equal to some multiple of pi. So it'll be, I'll start at pi. and I'll say plus pi k. Actually, I could just leave this as pi k, I think. I'll just do that. For any integer k. So if I plug in -2, -1, 1, 0 for all these, for this k value here, I'm going to get all the solutions to this. So then that means theta is pi over 2 k. Well, what I need to do is I need to grab just the relevant ones from this interval right here. I need to be from between 0 and pi. So if you plug in k equals 0, for example, you would get 0. If I plug in k equals 1, and I'm just going in order to get all of them, if I plug in 1, I get pi over 2 if I plug in k equals 1. And then finally, if I plug in k equals 2, I get pi. And that's where I need to stop, because if you go any more before this, like k equals -1, or if you go to k equals 3, our solutions are outside the interval that we need. So here are 3 other points, and these are going to give you the vertical tangents. So for example, I'll just do one of them. At this one, we'll just say this one. Theta is pi over 2. What's the r value where that occurs? Well, we have to plug in pi over 2 into this equation. So 3 cosine of pi over 2 is just 0. So we're just going to get 0 at that spot. I'm going to do one more. So we'll do this one. If theta is pi, go over here, cosine of pi is -1. So that point would be -3 pi. OK, so these are two spots where there's a vertical tangent line. There's another one right here. I guess for completeness, I'm just going to go ahead and do all of them. So if you plug in 0 for theta into this graph, you get 3 cosine of 0 is 3. So these are the spots where you have the vertical tangent lines. So now, does this make sense? Let's just quickly check this. So we just did a lecture where I taught you how to graph all of these basic polar curves. So r equals 3 cosine theta. That's a circle. We know it's on the positive x-axis because it's cosine and 3 is positive. And 3 is also the diameter. So your equation looks like this. The circle right here. This is 3. This is 0, 0. But I'm actually going to write these in polar coordinates. So let's think about this for a second. If I have r 3 cosine theta, which is a circle, if you plug in 0, the angle 0, you're supposed to get, let's look at our point here. So if you plug in 0, you're supposed to get 3. So this is the point 3, 0. Then what was our next point? Well, we have pi over 4. So at the angle pi over 4, we have 3 root 2 over 2, pi over 4. And if you continue along, the next one is pi over 2, which is supposed to be, when you go to pi over 2, it's 0 again. So it's right here. So this is 0, pi over 2. So the points that we generated, all 5 of these points, they are these points on the circle, the parts where you would get a vertical tangent line or a horizontal tangent line. So our answers are matching what the picture is. So look, this is where a vertical tangent line would be, right? Or this lowest point right here in the circle, that's where the horizontal line, or this is where the other horizontal tangent line is. It's at the extreme points up and down. And the vertical tangent lines are the extreme points left and right. So all the points we're finding, they're the points on these most extreme values, either up, down, or left and right. OK, so our last topic we're going to talk about is finding the arc length using a new version of the arc length formula. So I'll see you in just a moment for that. So the last thing I'd like to do is I'd like to touch on the arc length formula again, but now revisited in terms of polar curves. So recall that the arc length formula for parametric curves, when you had x equals some function of t and y equals another function of t on the interval a to b, was this formula. So you had the integral from a to b, dx dt squared, dy dt squared, where t was the parameter. Now, let's go back to those equations we were just using. So the equation was x equals r cosine theta, which was f of theta cosine theta. And similarly for y, it's r sine theta for the polar equation, which we're going to write as f of theta sine theta. So now our parameter is going to be theta, just like before when we're doing the tangent, the slope of the tangent line formula. So now, if you carefully make the substitution, so if we start with this equation right here, and we use our formula for both of these, and we do a careful substitution, we have the integral from a to b, the square root of dx d theta squared, because this time our parameter is not t, we're going to say it's theta, plus dy d theta squared equals. So if you carefully plug these in and do a calculation, you'll be able to show that the formula can be written as the integral from a to b of the square root of r squared plus dr d theta squared. So if you're given a formula r in terms of theta, so some polar curve now, you can use this last formulation to find the arc length. So this is the formula we're going to be using today. So let's try it with this example right here. What is the exact length of r equals theta squared? And here's my a. A is 0, and b is 2 pi. So the interval is going to be from 0 to 2 pi. Well, let's begin the formula. You have L equals the integral. It's going to be from a to b. So this is going to be from 0 to 2 pi. We have the square root. What is r squared this time? Well, our formula is r is theta squared. So r squared would be theta squared squared, which would be theta to the 4th here. What is dr d theta? Well, the derivative of r with respect to theta is 2 theta. So that's going to get plugged in for dr d theta. And I need to square that, because that's part of the formula as well. This is d theta. So then I have the integral from 0 to 2 pi. This is square root of theta to the 4th plus, remember to square both of these, plus 4 theta squared d theta. And this is equal to L. So L is integral from 0 to 2 pi. Square root of, both of these terms in here have a theta squared in common. So let's factor that out. I have theta squared. And then what's left in here when I factor out that theta squared, it's theta squared plus 4 d theta. Now, theta is a positive number. It's from 0 to, it's non-negative. So it's from 0 to 2 pi. So I'm going to take the square root of theta squared, and I'm just going to get the integral from 0 to 2 pi. Square root of theta squared is just theta. And I have the square root, and inside the square root, I still have the theta squared plus 4. To solve this integral, I'm going to do a u substitution. So we're going to let u be theta squared plus 4. So that means the derivative with respect to theta is 2 theta d theta. And then that lets me know that 1/2 du is the same thing as theta d theta. So let's make that u substitution. I'm going to change my bounds in terms of u. So the lower bound, if you plug in 0 for theta, you get 4 for u. And if you plug in 2 pi in for u, you're going to get 4 pi squared plus 4. That's the new upper bound if you plug in 2 pi for theta there. The theta d theta, you substitute that out and you get 1/2 du. And then we get the square root of u. That's all that's left. If you plug in u here, to make our substitution. So that's u to the 1/2 power. And now, taking the integral of this much easier thing, you get u to the 3/2, because I go backwards from 1/2. You put a 2/3 in front of it for the backwards power rule. You still have this 1/2 out front as a constant, and you're going to evaluate that from 4 pi squared plus 4 to 4. So from here, what I need to do is I need to plug in my bounds. So I have this 1/3 that's sitting out front, and I'll put a giant bracket. We'll plug in the 4 pi squared plus 4. That'll go in for u to the 3/2 power, minus, and then 4 to the 3/2 power. And what is 4 to the 3/2 power going to be? Well, you take the square root of 4 is 2, to the 3rd power is 8. And to make this look a little nicer, this is just kind of optional algebra. Notice 4 pi squared and 4 both have a 4 in common, so you could factor that out within the parentheses. So now I have 4 times pi squared plus 1 all to the 3/2 power. But then this 4, I can raise to the 3/2 power and get another 8. So I'm going to get 1/3 8 times pi squared plus 1. And the pi squared plus 1 is now just to the 3/2 power, and the 8 is not, because I raised the 4 to the 3/2 power, minus 8. They both have 8 in common now, so you could bring that up front. This is 8/3 times pi squared plus 1 to the 3/2 power minus 1. So that's just sort of a nicer way to write the solution for that. And then over here, I kind of just want to explore what the graph of this looks like, because you might encounter it. So what is the polar graph of r equals theta squared? It was not something that I talked about in a previous video. I'm just going to plug in a couple values for theta up to 2 pi, like we were doing here. Like, we wanted the arc length from 0 to 2 pi, so I'm going to plug in a few values. So I'm going to snap my fingers, and they're going to appear in this table. So here we go. So now I'm back, and you see all of these numbers here. So for example, if I plug in pi over 2 and square it, because that's the angle, you get approximately 2.47. When I plugged in 3 pi over 2 and I squared it in the equation, r is equal to 22.2. So what's happening is, as you square these angles, they're getting quite big, quite fast. And then how do these correspond to this graph? You might see that I drew this graph here. Imagine every single ring that I drew is 10, an additional 10 units. So you can count the r values by 10. It's 10, 20, 30, 40. I'd be amazed if you could see that in the video, but maybe you can. So each one is 10. So we start at 0, 0 in the dead center, so at the pole. Pi over 2, 2.4, is you're at the angle pi over 2, right? And you've got to move up 2.7, so 2.4. So we've barely moved. So starting from the angle 0, we're sweeping around in a counterclockwise fashion. So we go like this first. And then at the angle pi, you move out almost to 10. It's 9.8. So here's the next point on our path. So it goes like this. At 3 pi over 2, so at the 270 degrees, you go down a little more than 2 of the rings, so 22. So by then, I would be down here. And the r is increasing the whole time. So as you're going, you're pulling farther and farther away from the middle. So it's like this. And then one more would be 2 pi would be about 40, so about the last ring. So when I finally make it back to 2 pi on the right side, I'm almost all the way out there to 40. Oh gosh, I just totally messed that up. Sorry about that. But can you see the shape, or can you describe what that shape is? Imagine if you kept going. Because this grows really fast. This is actually a spiral. So if you ever see an equation that looks like this, it's actually just a spiral. You start at the center, and you just spiral, and it gets farther and farther away from the center, right? If I kept going, it'd be like that. It would just keep going out like that. OK, so I hope that was a fun graph to look at. As always, please send me any questions via email if you have them. Otherwise, I will see you in class. Have a nice day.